Welcome to the Literacy and Numeracy Secretariat's October webcast entitled Learning Mathematics Within Context. We are pleased to have you join Dr. Kathy Fosno and a study group of Ontario mathematics educators as they work through several strategies for teaching mathematics through problem solving. Dr. Kathy Fosno is Professor of Mathematics Education at the City College of New York, Director of Math in the City, and renowned author of numerous publications such as Young Mathematicians at Work and Context for Learning series. Over the past few years, Kathy's worked in numerous Ontario contexts with classroom teachers, math facilitators, coaches, math consultants, coordinators, and school leaders.
To get a full learning experience from this webcast, pause and play each segment. Use it to pace the mathematical activity of your study group. Engage in the mathematical work and professional discussion that Kathy facilitates as she poses problems, coordinates solution sharing, and asks questions. Use the participants' responses from the webcast as an additional ideas to analyze and discuss. This webcast will show ways that mathematics educators can deepen their understanding of teaching through problem solving. More specifically, during this webcast, you will acquire an understanding of the landscape of learning in terms of fractions and ratios. Experience different ways to solve mathematical problems in order to anticipate the range of mathematical knowledge and skills that students could demonstrate. You'll develop strategies for designing lesson problems with contexts that provoke students' mathematical thinking and learning. In preparing yourself for this professional learning session, think about these questions. What is the purpose of understanding students' mathematical knowledge at the start of a lesson? What's the significance of a problem context for students' learning of mathematics? Why is it important for teachers to solve mathematical problems that they will use during their classroom lessons?
There's been so much talk lately about how to use problems as a start, lesson problems, the idea of using context. I'd like to focus this session in the beginning on that and give you a chance first to just turn to the person you're sitting next to and talk about that. What does it mean to use context as a way to invite children to explore?
We talked about most of the mathematics used in the world today is based on a problem. It's not the math we do in class, it's the math we do every day. And how to engage our students in problems, it's easier for them if they see a real context to it. Otherwise, why bother?
So a lot of your thought behind this is that the context makes it easier.
It gives them a stepping stone into the problem.
Okay. Other thoughts on that?
I think that it makes it real to the students, because I think too much of the math that goes on in classrooms is decontextualized. I also think that by putting it in a context, it gives you an opportunity to bring in things like estimation beforehand, so that the kids have an overall picture of what's going to happen with the problem.
Context is important because it lets children have a measure of sensibleness, I guess is the word I'm looking for. It gives them something to keep in mind while they're solving the problem, something to continually check back on, which I think is a really important mathematical skill. Well, it seems, as I engage in a problem, it seems like I'm starting to work it out, but I can't tell if it's making sense, or I don't have any way to judge, even if it makes sense to me, if there's no context around it.
That's really what we were talking about as well, and just that making it relevant to children so that they can understand it, that they see math as around them every day, that it's just not a 40-minute math period or a 60-minute math period every day, that mathematics is everyday living experience. And we were talking about how important that was for kids.
We spoke about how it's important that students see mathematics as part of everyday living. And also I was just thinking as I was listening to my colleagues that we need to have something in place that helps them to make sense of the math that they're doing. And also sometimes a context allows you to choose a particular way of solving a problem, which you may not have done if you just use a straight procedure. So the context often defines how I'm going to work the mathematics, how I'm going to use what I know to solve a problem, And sometimes it can be something I already know that will lead me to deeper thinking if I'm working with a context as opposed to practicing a procedure multiple times.
And we were talking about that. We were also looking at how a good problem will also activate prior knowledge within a context. Students can go back and look at and think about what they have done before, and then start making those connections to the mathematics, to their real life, and the whole relevancy.
I'm also thinking that a context that is tangible can be actually physically explored by students. So for example, I'm thinking of a problem that you gave us before about measuring a tarmac for a playground. You can actually go out and step through it, walk through it, and get really a sense of what the mathematics is to solve the problem. And it's very much similar to what you said, Mary Lou, that it actually gives them a sense of sensibleness about whether or not their solutions or ideas are doable with a real tangible object.
So I'm hearing consensus, I think, amongst us in regards to how context can be used to help children realize what they're doing, that it helps them build connections to their lives and perhaps even to see their lives in ways that are mathematical. What I'd like to explore is how context might also be used over time by crafting sequences of problems that are going to ensure that mathematical development occurs. If we only just give rich problems, they may help children realize what they're doing, but all we are bringing up front are their conceptions at the start. Of course, what we want to do as teachers is develop mathematics. So we have to look at how do we use context in ways that are really going to support development over time. Over the last 5 years, I've been filming exemplary classrooms that I've worked with in New York City. And the filming has now been put on CD-ROMs, and I can actually transport you through this technology to a classroom, and we can do some lesson study together, examining what a teacher is doing as the teacher uses context, and we can explore the children's work. So I'm going to take you there now. I'm taking you to a grade 6 classroom. The teacher's name is Joel Spengler. The children have done prior work with fractions. They have a fairly well-developed understanding of a fraction as a part-whole relation. They've done some exploring of fractions and the connection of fractions to division. Joel is working on a problem that is going to invite them to explore equivalence more deeply. So I'm going to now take you to the classroom. We'll see Joel introduce the context.
So since we're thinking about situations in my life, I've got another situation I want you guys to help me think about. Some of you know that recently I just bought a kitten. When I picked the kitten up from the animal shelter, they said to me, which I didn't know before, kittens have to eat a special kind of kitten's cat food. So I found 2 stores in my neighborhood, a store called Bob's Store and a store called Maria's, 2 little bodegas in my neighborhood, that both sell this kind of cat food. The problem is, at Bob's Store, they'll sell me 12 cans for $15. And at Maria's, they will sell me 20 cans for $23. So I could go to either one of these stores. They're both in my neighborhood, but I want to figure out which one's the best deal for me. Helena?
Well, you could think about how many more cans you're getting at Maria's store and if it really makes a difference in the price, but that also kind of reflects on how much each can costs.
So that still kind of comes back to how much each can is? It's the same brand of cat food, same size cans. They just have 2 different offers for how much they cost. So are there any other ways you might think about this? Jeremy, what do you think?
Well, you could try and see how if you can make like an equivalent fraction maybe, like 3 goes into 12 and it goes into 15, and then you can try to see if like a common fraction or something.
So you're going to try to think of both of these as fractions?
Yeah.
And then try to find some common fraction for both of them, common denominator? Okay. Chloe?
Well, you could use like the 15 is sort of like 5 can go into it. So you might say 5 out of the 12 cans would be how much money?
So you could think of chunks of cans?
Yeah.
Or chunks of dollars? Like 5 cans is this much, or $5 will get you this much?
Might take less time than finding out how much one
Okay.
can costs.
All right. Just by show of hands, can I just see all people who feel like they have a way into this problem?
I'd like you to explore the problem a little bit. Did anyone write the numbers down as we went through? I know you were, yeah. Kathy, you want to just tell us the numbers again?
For Bob's store, it was 12 cans at $15. And for Maria's store, it was 20 cans at $23.
All right. Work on your own, and then I'm going to give you an opportunity to turn and talk to the person you're next to and share your strategy. Okay, tell me what you're doing here. So this is $12
So that was the
or
12.
12 cans.
That was the 12
which is,
cans, right. That was the 12 cans.
and so you're dividing the 12 cans by the $15?
Yeah. So it's big, yeah. I was just listening to what
Okay.
you did. Thanks for pointing that out.
Okay,
because that's
okay. So what did I point out? I didn't know. I thought I just asked you what you were doing.
Yeah, 12 cans, yeah.
So what is it?
So-
What insight did you have? Sounds like you want to change your strategy.
Yeah, and actually, when I started doing this, I thought, now I'm getting into division, which is fine, but I think I want to change my whole strategy, but I'm not just sure which way I'm going to go
Okay,
now.
I'll give you some
'cause
think time. Turn and talk to the person you're sitting next to now and share your strategy. Let's see if we can find a variety of different ways to attack this. So you use 60 as a common whole, and what you did is just say, well, a dollar just gives immediately $12. I've only got to worry about the $3 that are left, and 3 divided by 12 will give me the 25 cents. And you did the same thing here. So here you have 3 divided by 20.
Yeah, and I didn't even go as far as you did. I just said
I started
between
with
12
trying
and
to
15.
think
So
of ratios.
they're
So I was
more than
going-
$1 a piece. I know
But I
that.
could step the
It's
numbers,
12
because I was
and
thinking
15.
12 over
There's
15
three
and
different.
23 over
Three
20.
different.
So this is 12 cans, right?
Mm-hmm.
And you want to
Yeah, I don't
divide
know
the
how to
12
divide by
cans by the dollars?
It would be the dollars by the cans. It should be 15 12s.
What do you think, Mike?
I
Which
agree.
is it?
This,
Yeah, we want to find the unit rate, the cost per one, so you'll be dividing 15.
Yeah.
See,
And
and that's a
here-
natural mistake, I think, because when I wrote the fraction 12
11.5
fifteenths,
by 10.
and you start dividing, then that's when I realized, oh,
Yeah.
that's wrong. You know,
Yeah.
See, and I had
Yeah.
12
So that's not
15s, and I was
automatic.
trying
So
to
did you
double
go to find the
ratios.
cost of 1 can too, Mike?
So-
Was that your strategy?
I thought if you could, if you
Can we start off with you, Dennis? Would you just use this first paper up here and just write down use the division strategy, right? And you found the cost of 1 can? Just put your division strategy down first, because that was the primary strategy you ended up using and the one you talked to Kathy about. Okay, before we go any farther, are there comments or questions about what Dennis has written? Mary Lou?
I'm not sure why you're dividing 12 cans by $15.
Unit price.
12 cans, so it's decimal 8 of a can for $1. Is that what you're figuring out?
So you're dividing
Okay,
the
so-
cans by the dollars? Tell us a little bit more about that. Why? Is this, because I thought I heard you say earlier you were going to find the price of 1 can. But would you put yours right next to Dennis's, because you also divided
Right.
it? And then we can explore the two next to each other and talk about them.
Okay. So, knew that, I knew the cost was $15, for 12 cans, $15. So I want to find out what the cost of 1 would be, so I divided that by, 15 divided by 12, and I got 125. So the cost of 1 can was $1.25
At Bob's.
at Bob's. Now, what I did is, I looked at the next numbers, and I saw 23 divided by 20. Oh, that's too complicated. That's too much. So I thought, well, what if it's $1.25 per can of Bob's? How much would that cost for 20? So I took the $1.25 and multiplied that by 20, and that would give me $25. Wow. So at Bob's, to buy 20 cans would cost me $25. So to go to the other store and buy 20 for $23, that would be a better price.
Okay, before we go any farther, so you ended up deciding 20 would be a nice thing that you could use without having to divide the other one. Let's go back to the issue of division again. What are your thoughts now, Dennis, on are you trying to find the price per can the price, how did you put it, Mary Lou, when he was?
The amount of can that you would get per dollar.
The amount of a can that you would get per dollar.
Because it's 12 cans for $15, so if it's 0.8, it must be for 1.
So in your instance, the way that you've proceeded, it would be 0.8 of a can
Per dollar.
that you could get per dollar. And then you followed that through for Maria's?
Yes. For Maria's, 23, 20, and I got 0.71, I hadn't finished it out, but as soon as I got to 0.7, I realized that it was a cheaper price.
So you get less of a can
Per dollar.
per dollar. So is that a cheaper price or a more expensive price? Turn to the person you're sitting next to and talk about this. And as you talk, let's compare it to the division that Mike did. Mike is trying to find the cost per can. So both people have divided, but their quotient has a different meaning.
It's a really nice way to put these as ratios. That way you know this means 23 divided by 20, and this means 15 divided by 12. It's a nice way to check. Now the question is, what does this mean?
Unit rate per can.
71.71 is worth $1. 0.8 of a can is worth $1.
So you can do both.
Or it costs $1.
What you're measuring,
Right.
We don't get the same result.
Yeah, I didn't.
Okay, the numbers are wrong.
All right, Dennis, I overheard you say, oh, I made an error. Would you go up and just tell us what you did and what you want to correct?
The first error was, I thought I was doing unit price. And then listening to Mary Lou, I realized I was doing, actually looking at how much $1 would buy me of a can. And the other error is here, this, 0.86 instead of 0.71. And that was just a straight division error. And this way, it still shows Maria's gets a better price. We get more of a can for $1 than you would have thought.
Did you use a calculator to derive those two decimal quotients, or did you do the long
pencil
division?
paper.
All right, would you actually follow through with the whole long division? Do you mind?
And you want to continue more?
Yep, just so we can follow it all out. It's so easy to make a calculation error when we're dealing with pencil paper strategies that are with numbers not quite so friendly. It wasn't a friendly long division problem. There's so many opportunities to make place value mistakes, to make calculation mistakes, and as we go through an explanation of the variety of strategies that many of us used for this problem, it'll be interesting to look at which are friendly, which are easy. What could we do mentally? Do we need the pencil paper algorithm? Did we even need to go to one can, for example?
Kathy, what's interesting to me is that even though we had some error here, I had never thought, I was trying to do unit rate, but I had never thought that if I did it the other way, it would still tell me what I wanted to know. So this actually helped me seeing this, because I thought of it differently than I had before.
Your strategy actually does work. It's just, it took you a long time to do it. You had to think out, what's my quotient really telling me? What is the rate I'm actually figuring out here? And the process of exploring gave you an opportunity to revisit that, which is a way of deepening your own thinking and the rest of our thinking too, I think, because many of us are saying we never thought of doing it. Okay, thanks, Dennis. Mike, let's go back to yours. I wrote, if you notice, when you were talking before, there's some more print up there, Bob's, Maria's. I went up and added that when you were all doing pair talk. Would you follow out with Maria's, even though you found that you didn't need to go in that direction? If you had done the unit price for Maria's using the division, you would have divided the 20 into 23.
Right.
Right? Can you just write that? Mary Lou, you said, no, I don't see that. Talk out loud.
Because I'm thinking, isn't 23 the dollars and 20 are the number of cans, so I guess that is right. I was looking at 23 over 20 because I did it as a fraction.
Is there
But
any
I see
difference?
it- No, I see it now. Yeah.
So if we had written underneath, what you just said is this. This is just a different way of symbolizing this.
Yeah.
This
yeah.
in fact means divide.
So, so then I said, so this is the same as 11 and a half over 10 because it took half of this and half of this. So then I needed this to be in money. So I had to see the half as decimal 5, and so I knew when I divided I would get 1.15.
Dan and Kathy, you both use 60 as a common whole, right?
Yeah.
Would you just put your, Kathy,
Okay,
in line?
20 cans at $23. So with this one, I multiplied by 3. So it's 60 cans at $15 times 3. $15 times 3? How did I get 5?
You actually multiply by 5.
No, it's by
3.
5. By 5. This is by 5. So it's 12 times 5 is 60. Then 15 times 5 is $75. And then this one here, because I want to get 60, I multiplied times 3. This one is times 3. So 20 times 3 is 60 cans. And that will cost $23 times 3 equals $69.
Mary Lou, you did it a very different way. Would you share your strategy?
When I looked at 12 cans and 15 cans, or I mean 12 cans for, 12 cans for $15. I realized that it was more than $1. So first of all, I said that they're gonna cost more than $1 each. So 12 cans for $15, there was a $3 difference. As if they had cost if they cost $1 each, it would have been $12, so it was $3 difference. And then when I thought about 20 cans for $23, I saw that same difference. So there's $3 difference there, and there's $3 difference there. So then I thought $3 over $15 compared to $3 over $23, this would be cheaper. No, this would be cheaper because I have to spread the difference, that $3 difference, over the cost of 23 cans, and that $3 difference only over the cost of 12 cans. So that's when I thought, okay, so that's going to be a quarter. So that must mean that these guys cost $1.25, and that's when I had trouble with this one.
I think actually when you were working, you said, I don't even need to go any farther. Is
No,
it 3
I
for
didn't.
23 or 3 for 20? Which do you mean there?
Oh, 3 for 20, right, 3 for 20. Thank you.
Mary Lou, how did you get the quarter, how did you know it was a quarter again? I missed that.
There are 12 cans for $15, so if they cost $1
And actually, I have
each.
to ask you the same question. I'm sorry. Is it 3 for 15 or 3 for 12? What do you want the 15 there or the 12?
I do, sorry.
Well, let's talk about this. What
Yeah,
does she
you
want
might-
there?
You She's spreading out along the cans, so she does want
The cans.
All right. So if you take out that whole dollar, you're left with $3 will buy
12. $3 will buy $3 spread over the cost of 12 cans. So I have to add that to it. So that's going to be $0.25 each. I didn't go there actually. Initially, I just said 3 spread over the cost of 12 cans compared to 3 spread over the cost of 20 cans. No, this one will be cheaper.
So you didn't even have to calculate it out any farther. You just said
That's right.
3 for 20 versus 3 for 15.
Yeah.
I can tell which versus 3 for 12. I can tell which is a better.
And in fact, when I went back to figure out the cost per can, I went back to these fractions. And that's actually, I had done 12 cans for $15. So I knew that 4 cans, if I divided by 3 here and 3 here, it would cost $5. So then I could easily make this 20. So I knew that these 20 cans would cost $25.
That was
So
using
that was
20
my
as a
third,
common.
yeah, another one.
Okay, I'm going to put a chart up of all the different strategies that you just shared. And let's try to fill out this chart together. So here's Bob's store. Here's Maria's store. And let's use a T-chart. And let's say this is the money. These are the cans. So let's put down what we know so far. We know from the beginning of the problem that Bob's, we can buy $15 for 12 cans, right?
Yeah.
We know at Maria's that it's going to cost $23 for 20 cans. All right? When Dennis shared, what can we tell from Dennis's work?
That for $1,
For
at
$1,
Bob's, you can get 80 hundredths of a can.
Okay, what do we think? Agreement? Yeah? All right, and what can we tell about Maria's?
For $1, it's 86 hundredths of a can,
Plus.
plus,
In fact, we had.
Probably 87.
approximately.
All right, what else can we tell? Let's go to Mike's. Mike, what did you tell us?
Well, I found out that for $1.25, I can buy 1 can.
For $1.25 at Bob's, you can buy 1 can. And at Maria's?
By continuing on what we did find out from other folks, I didn't actually do the calculation, but for $1.15, I can buy 1 can.
Okay. You also worked with 20, right?
Right.
So let's get your data up for 20.
So that was at Bob's store. I found that 20 cans cost me $25.
And at Maria's?
I didn't need to do that because we had the information, 20 cans would
We
cost
had
me
it.
$23.
Nice. Okay. Kathy, what did you, and we didn't have you come up, but your strategy was identical to Kathy's. Kathy, what did you add?
So 60 cans at Bob's is $75. And Dan, did you get the same thing, 60 cans at Maria's?
For 69, yeah,
What'd you get?
$69.
Oh, okay, I could read my writing. Okay.
Okay. And Mary Lou, what did you add? You didn't need to worry about one whole thing. You dealt with the 3. So now, were you working like Dennis, figuring out, was it $3 or 3 cans?
I said 3 cans would be $5, so I divided by 5. Money by 5
So 3 cans,
would be $5.
is it $5? Or is it $3 left for 12 cans?
In fact, it should be, what I kept thinking of is the 4 cans cost $5. I divided by 3 and I divided by 3.
That's down here
Yes.
with, okay. So now let's shift to children and to Joel. Why might Joel be using this context with his 6th grade classroom? And let's take a look at these numbers. Why these numbers Do you think these numbers were random? Were these really the numbers at the store, or did Joel choose these numbers? And if Joel chose the numbers, and actually I'm going to tell you he did.
Yeah, I'm sure you did.
He chose it with me and with Martin Dolk, my co-author. We carefully planned this problem, and it's within a sequence of problems in a unit that we call best buys, ratios and rates. What did they support the development of? Joyce?
Well, I found they sort of lend themselves to moving away from strictly division because the division was not comfortable. I don't think children like those kinds of numbers. So
Children or all humans?
Myself included.
I heard Dennis say very loudly and clearly, I wish I hadn't gone that way.
I know, because my first inclination was try to double numbers to try to get maybe to a 20 I could compare. And then I saw people divide, and I thought maybe I should divide. But we struggled with, I think, how to compare them without going through the messiness of the division, which might lend itself toward thinking in ratios maybe, or comparing differently, looking at equivalence in a different way with fractions.
If you look at Kathy's method, look at the numbers she made on 5 and 3, which are very easy numbers for the kids to use.
So there's some nice common multiples here that could be used.
But they're not direct multiples of each other. So I think that was deliberate, and I think that $3 difference was probably deliberate too.
Yes.
Or that $3 difference between the number and the.
And look at the fractions that it produced with the $3. If you did Mary Lou's strategy and you took the dollar out, you were left with $3 for 12 cans and $3 for 20 cans. Nice fractions again. The kids could begin to look at 3/12 as a fourth.
And maybe visualize.
A 20th is a nickel. So with money, the numbers work nicely to allow children to support the development of multiple strategies. All right, so now let's shift. What strategies do we expect children to use? This is grade 6. They have done some work with fractions. I wouldn't expect that their understandings of fractions are real flexible yet. But you heard them talk about fractions. You heard them say something about maybe I'll find a common whole. So they do have some understanding of fractions. Do you think they'd have similar strategies to yours? What might they do?
Kind of parcel out. They might knock off the 12, because they know, and then they would get to that 3 again. Similarly with the 20, they might knock off the 20. Well, that's $1 for a can, so what's left? They might, I could picture some students I work with doing that.
And in our grade 6s would do some ratio tables, because I know the grade 5 expectation says that they will do some show some understanding of proportional reasoning using integer rates. So they would have probably worked in a kind of ratio table previously.
So we might see some of the children using a ratio table. How do you think, though, if they use a ratio table, any thoughts on what they'll do with the ratio table? Like, where would they bounce?
Yeah, I don't think they divide. I think they go immediately to the 20, 40, 60, and the 12, 24, 36 to 60.
I wonder if they'd use a number line and try to put ratio on top and ratio on the bottom, like try to find what 10 cans were. So, for instance, they might be able to try to figure out whether they would do it effectively or not. But I think they might, some of their comfort is with jumping across number lines. They might try something like that.
So common wholes, you think one possibility might be 10 cans? And you're suggesting they might represent, use the number line almost as a ratio table. So we could use a T-chart as a ratio table. We could literally do a ratio table with columns and rows, cells, and we could use a number line almost to represent the ratios. All right, out of curiosity, how many children in the class do you think are going to solve this problem? Would you say 10%, 25%, half the class, 75%? 90%, 100%. This is normal public school, urban school in New York City. It's in an area of New York that is fairly mixed It's some of the families there, it's in the lowers, near the old, in the Battery Park section. I'm also thinking about what might strategies be, regardless of the children and their backgrounds. Didn't we earlier say that there were many different strategies that could be used?
Right.
One that you listed, Joyce, in fact, was even drawing the cans.
Yes.
So now, if we say that there's multiple entry points here, many different ways for children to solve this problem, it may surprise you, but 100% of the children in this class solve the problem. But of course, they solve the problem in a variety of ways. I think so often we make assumptions about children, about their backgrounds, about what they can or cannot do. We think a problem may be too challenging, when in fact, if we are inviting children with genuine context to solve problems in their own ways, there are umpteen ways children can solve the problem. There are many entry levels. I want to examine the children's work with you. I'm curious if you have any thoughts about what Joel might be trying to accomplish with this problem.
Reasoning.
Proportional reasoning, jumping around the ratio table maybe, huh? Dealing with common wholes, not always going to the unit price. So let's take a look now at a few of the children. I'm going to pull up Chloe and Josie. We'll take a look of them at work, and then I'll show their work.
4 cans for $5, right? Because you can go 4, 8, 12, and 5, 10, 15.
Write it like
right?
this. Write it like this.
Yeah, you get that?
Yes.
Okay. And so that would mean that you would have
Wait.
each can would equal $1. And then we have, because if you did 4, so it'd be 5 minus 4, you would have 1 left over, right? So you have to break that 1 left over. You have to break it up 4 times so we can fit it into this 4. So you can.
I get how this is $1.25. $1.25. Okay, I get that. So how'd you get there?
Hold on, but okay, it'd be 4 cans for $5, right?
Oh, now I get it.
And then so if you did 5 minus 4, you'd have 1 left over. That 1 you have to break up 4 times, right?
Okay.
Because you
So
have
5
4
minus
cans.
4 equals 1.
And if you do 1 divided by 4, you get 0.25 or 25 cents, right? Right?
Yeah.
So the $1 and the 25 cents equals $1.25. That's how much 1 can would be. So Maria's is.
I see. But where'd you get the $1 from?
Because if you take the 5, you have to automatically give $1 to each can, and you just have $1 left over. Right?
$1 for each. So I'm gonna put this in here. At least $1 for each can.
It has to be $1 for each can for the 5, and then you'd have 1 left over. And so Maria's is a better deal because it's $1.15 for 1 can, and it's $1.25 at Bob's. So where you took the 15 for 12, and you were left now with take $1 out. I've got 3 for 12. Let me divide my 3 by 12 to get the 25 cents. She says think of it as 5 for 4. So that means pull the $4 out. I've got $1 left. Divide by 4. That's a quarter too. So $1.25. You can see what they're writing. There it is. Anybody want to comment on what they see there? Ask a question.
Still feels different than Mary Lou's, because you use the word the difference, leftover, divide among. Even though the dividing among is still the same idea, it feels more like partial quotients, where you have the $1 divided among, then what's left divided among. Almost like a 2-step division.
Is that what Mary Lou did, though? Mary Lou said 20 divided by 20 plus 3 divided by 20.
I guess it's the same idea. It's just that you said difference.
that you're focused on the difference, but they're having like a two-step division thing. But really, it's the same idea.
Yeah, because they've written 5 minus 4 equals 1.
And
then
if,
divide.
although you didn't write it,
Yes.
you would have said 23 minus 20 equals 3.
Yeah.
So then you would have divided the 3 by 12.
Yeah.
They divided the 1 by 4.
And it's interesting how decomposing numbers was so important to what they were doing, because they could easily split apart the numbers comfortably, and so that wasn't an issue. So decomposing in their minds seemed really important for that.
Especially with the money context. To decompose the $1, the $4 once, and then the $1 to quarters, it just made sense.
Made sense to them,
Yeah, well, that one just feels weird, 3 over 20. But you're right, it's the same thing.
All right, let's take a look at Elit and Veronica. And I won't show them at work to save time, we'll just look at their work.
Oh.
So take a minute to look at it, see if you can figure out what they're doing, and you can turn to the person you're sitting next to and talk about it if you like.
So it's $15, here's your dollar, and 12 cans. So it's like every dollar, divide them among the 12 cans. And so it's iterative.
12, there's 12, and there's 3 left over.
Yeah.
And there's 3 left
Yeah,
over.
there's 12, there's
So
12, there's 12, 12.
That's nice.
Can you just describe what you see first? Let's see if we can even agree on our descriptions, and then we'll try to make some sense out of what they're doing. They've drawn something. How many parts have they cut it up into?
12.
Any other noticings on there? What is this down here?
Well, it's a total of $15.
There's a total of 15 altogether, so they've drawn 15. And
$1 per.
what's this piece right here? See the caret that they've drawn?
That's the
And it
$3.
says extra dollars.
So that's the
So there's
difference.
$3 that are extras. What's this down here?
3 12ths of.
It's a mixed number, 1 and 3 12ths.
In their own informal
Yeah.
notation,
Yeah.
of course, it's incorrect the way they've
Right.
written it here, but in some sense, they're saying everyone is gonna get $1, so
Yeah.
like your strategy,
Yeah.
Mary Lou. There's $3 left over. The 3 needs to now be divided by the 12, so everybody's gonna get 3 12ths. They don't know what that is in terms of coinage. The numbers are tiny here and difficult to see, but that's an 8 1/3. They tried to figure out, what do I have to multiply by to get this to $1, so I can figure out.
Wow.
Because they didn't recognize 3 12ths as a quarter.
Now, this piece of work is interesting, because Mary Lou, you told us earlier you didn't have to calculate the unit price. So, did they?
They certainly didn't with their first drawing, no. And they took that difference of 3 off.
But they ended up fully calculating to the cost of 1 can.
Exactly.
Now let's go back and look at Josie and Chloe as well. Even though they did the 5 for 4, they didn't look for a common number of cans. They went from the 5 for 4 down to the price of 1 can. So no matter what the strategies are, they're going for the price of 1 can. And here we see the same thing. Beautiful thinking to get there. But still we need to go to the price of 1 can. Let's take a look at Corinne and Layla. Here's their piece of data.
They're having, when they have 15 to $7.50. So they're having, and having again, and then having again. Interesting.
Joyce, talk out loud. What are you noticing?
I'm noticing that when they started at Bob's store with 12 for 15, they took the 12 and they halved it. And when they halved it, they also halved the 15. So 12 divided by 2 is 6 cans, and for 6 cans it's $7.50. Then they halved again, 6 divided by 2 is 3, and those 3 cans cost $3.75, and they got it down to 1 can, which was $1.25. So they ended up finding the unit cost for 1 can.
What Joel does, he breaks the class up into 3 groups, 3 meeting groups, and the children run the meeting groups themselves. This is a precursor to the Math Congress. In the small groups, they talk and they share their strategies with each other first. A little bit, perhaps more risk-taking can happen that way, a little bit more willingness to talk without needing to get up in front of the room with your poster and share your work. So we'll look in on one of these meetings.
We were dividing the cost, the cans and the cost for each one in half. So like for 12 cans for $23, we divided the 12 cans in half, and we got 6 cans, and we divided $23 in half. I mean $15 in half to get $7.50, and we just kept on dividing until we got to 3 cans for $3.75, and then we just divided that by 3 to get to 1 can for $1.25, and we divided $3 by 3, which got $1, and 75 cents divided by 3, and we got 25 cents.
I have a question. Did you just pick 12 divided by 2? Is that you just picked it, or like what did you start with?
We started off with 12 cans, like that, and then we divided it by half.
Why did you divide it by 2 and not by like 4 or like 6?
Because we thought it would be like much easier to get to the next one. And we thought it would be easier to get to 1 can from doing that pattern.
I have a question. Why did you divide 3.75 by 3?
Because we were trying to get to 1 can, the cost for 1 can.
Yeah,
so what we did to the cans, like we divided that by 2, we'd have to divide the cost by 2.
Like see which.
And then we switched to 3, so we get 1 can, and then we get to the next price from there.
Oh, okay. So you switched. Okay,
Yeah.
I got it.
All right, comments? Maybe a paraphrase on their strategy?
Ratio was all the way down, first by half until they got to a number that easily divided,
So
and
that
then they got
half
to 1.
is so nice, right?
Yeah.
If I just have first, I can do that. That's nice and easy. Let me have again. Let me have again. Whoops. Okay. I can't have anymore. What could I do to get to 1? And the same with the other one. What could I do? They end up at 5. What could I do to get to 1? Still the need of all these children to get to 1 can. Now, if we think about fractions, now not in grade 6, in Canada, I think you do addition and subtraction of fractions in Canada, grade 7, 8. But of course, at some point where this class will be heading, the 7th grade teacher hopes, is the kids to have a strong sense of equivalence, so when they move towards using common denominators, they'll be able to use common wholes. A strong sense of equivalence is needed for that. Joel is now going to have a math congress. Now, in the math congress, he's going to do something similar to what I did when I had you get up and tell us your strategies. He has a class of 32 children. He's not going to have every pair get up and share their work. First, there's not enough time, and secondly, many of the strategies will be redundant. He's going to pick some strategies, and he's going to orchestrate a congress that he hopes will support development. Now, I'd like you to use sort of, although we've only looked at 3 pairs, I will tell you that there is another group in the class that has used 60 as a common whole, but only 1 pair. And other than that, although there is the ratio table strategy, as we just looked at, there is also the unit division strategy. A lot of children just divided to find the cost of 1 can. Now, if you were Joel, and you're going to orchestrate a math congress, a place where powerful talk will happen to be supportive of development, what strategies might you like to have a conversation on? Which one would you share first? Which one would you share second?
We thought we'd start maybe having the kids share with sort of the having strategy, first of all, because that was a great strategy of showing that relationship as a nice, easy number for the kids to work with. Eventually, in our mind, we don't want to jump right into the division process. We want to kind of end with that. And there was a couple of reasons for that as well, just so we could show all of the strategies. There would be a lot of children who might have jumped to that strategy right away thinking, oh, I think that's what we're to do. And there'd be some children who know that that's what you do and understand it fully. But there might be some kids not really knowing why you have to do that operation, where if you can show some of these other strategies that kids used, it would also help them fully understand, oh, that's why we do that. So we thought maybe this having strategy would be a nice one to start with.
Because we thought since most kids started with the division, maybe you want to start there and then move towards the more proportional ones that shows the more proportional reasoning more clearly. The other way is to start more with the ones that are more proportional, such as the ones going to 60, which is really, in many ways, sort of almost the simplest one. I think that's why I chose it. And and move up and move towards the more abstract one.
Dennis and Kathy, what did you talk about?
The focus of this was to develop understanding of equivalence. And so equivalence in the most unfamiliar strategy or context or use of calculation would be something that you'd want to move towards as just unfamiliar. At the same point, I think you just can't go by frequency responses. It's about knitting together the mathematics to build collective understanding. And so you think about what's the goal of this.
There's a bit of a disagreement, too, amongst the three of you that I want to tease out a little bit. Because, Dennis, I heard you say, I like to start my math discussions with some of the sample strategies that I think everybody in my class is familiar with, and I like to have it end with one that is very different. What I just heard you say, Kathy, and I think this is somewhat similar to what you were saying earlier, Joyce, is I want to scaffold the math development. So it's not familiarity versus unfamiliar as much as it's which piece could I use first to provide a bridge for the next piece? Which piece would I use next to provide a bridge for the next piece? Now, of course, we might not always want to scaffold it that way either, because kids will be very savvy and always know, why is she always picking me first? I must have the worst strategy here, which, of course, is not the case. We might sometimes want to orchestrate the Math Congress around some powerful, big mathematical ideas, like bouncing around the ratio table. What are some common holes we could use? So there's many, many different ways to go in terms of how to scaffold this Congress, how to structure it. If only it were so easy to just have a recipe and we'd all know, okay, now this is how I'll do my Congress. There is no one right way. We'll look at what Joel does. To save time, I can't show you the whole Congress, it's too long. The Congress lasts about a half an hour. Joel picks a unit division strategy first, and he has a pair come up and show how they divided and how they found the cost of one can. He has a second group come up that has used the ratio table and done 5 for 4, the same way that we saw Corinne and Layla we looked at. Now, after they come up with their posters and they convince the kids in the class that their strategies worked, Joel does a recording on the side, much like what I did with you. He pulls the numbers out of all the things they said, and he makes a ratio table chart for both stores.
And one can was $1.15.
And then he pushes further. We're going to come into the Congress as he pushes further so we can see the math that he is trying to develop.
Can you ask your question so everybody can hear it?
I said, how when you were dividing it down, how did you know that you would stop at like 125? Or
We kept dividing in half until we got to one can, because you can't buy like half a can.
So you divided in half for cans and the price in half?
Yeah, but when we got to 3 cans, we couldn't divide it in half, so we divided it by 3.
Does that make sense? How many of you understand what Dylan just said there? Yeah? Questions about that? Ms. Simcoe.
Why did you divide it by 3? Because you can divide 3 in half.
You can't buy 1.5 cans.
Are you saying from the 3 cans to the 1, you're wondering this jump from 3 cans to 1 can? I just want to clarify what you're asking. Why not?
Like, why not divide $3 by 2, not by 3?
Can you answer that?
Because if you divide by 2, it would be 1.5 cans, and you can't buy 1.5 cans of cat food.
Do you hear the difference in the way you guys are talking about that 3? Ask your question about 3 again.
Why didn't you divide the $3 by 2?
And what are you calling the 3?
The can.
Can. So you were asking about $3, but the 3 in this case is actually the number of cans.
But then why didn't you even divide it down to 1? Because you knew that there are 12 cans.
But we have to get down to 1 to find out the price, so we can multiply it up to 20, because we can't go from 12 to 20 accurately.
But how did it help you?
Because it's more accurate than 1 can. We wanted to see what would have a better deal with buying 20.
When you had 1 can, how did it help you to have, like, how did it help you figure out the price when you had 1 can?
It's the price of 1 can. You go down, you see which her store is cheaper, and Maria's store was $1.15, Bob's $1.25, so Maria's was cheaper. It helped clarify which store to go to.
Yeah, but why did you divide like everything in half? Because you could just say we have 1 can left, and I just don't understand why that would help you figure out the price. Because if you just pretend that you had 1 can left and figure out the price from there.
Because we wouldn't know the price of 1 can if we just guessed. We had to go down and make both stores have 1 can to see, because we can't compare 12 to 20 cans, because it just wouldn't be accurate.
Is there somebody else who feels like they understand the system that Dylan and Tristan used that maybe could put it into their words? Maybe another voice in here would help us clarify this.
Their strategy was to divide the number of cans they had by 2, and then that would make the price, that would divide the price by 2. So to get to 1 can, their strategy was to keep on dividing. That's how they got to 1 can. That's why they did all that.
So they divided the price when they divided the can too?
Yeah.
Okay, I get it.
Any more questions about this strategy? No? Let me see the hands of people who feel like they understand it. Here you go. Okay, thank you guys. I'm gonna keep track of the things that they did in a slightly different way than they did it. I'm gonna put it in a T-chart, and I want to be able to see the number of cans like they had, and then also the price. They started out at Bob's store with 12 cans, and that was $15. And then 6 cans was $7.50. And then 3 cans was $3.75. And then finally they got down to 1 can, which was $1.25. You with me?
Yeah.
For Maria's store, I'm going to keep tracking the same way. Number of cans, cost for that many cans. Started out with 20 cans, $23, 10 cans, $11.50, 5 cans, $5.75, and then 1 can was $1.15. Can you take another few seconds and turn to the person next to you and see if you can just explain to each other how these tables help us keep track of
His goal here is that proportional reasoning. And have we perhaps stopped that kind of development in our schools by treating every topic as if it's totally discrete? Fractions are taught here, proportional reasoning is taught here, unit rate is taught here, and addition of fractions will be taught here in grade 7. So it's as if there's no connection between all of them, when in fact they're all related. Too, I overheard you say something about, because they're doing it in their own way, the procedure's not getting in their way of thinking, and it's powerful, the proportional reasoning that they're
Absolutely.
using.
And actually, that bouncing around the ratio table, that's what it was. They were just bouncing around. But in grade 7, we work on this thing called scale factor. And they were doing that without giving it the term, and so flexible. And again, when I heard Mary Lou be amazed with 1.5, they're using 1.5 times. I mean, in grade 7, they would have difficulty with that.
And that was Veronica, who we looked at her work. She was the one that did to make it into the 100 multiplied by 8 1/3. That was the piece of work we looked at. So she's able to do the scaling up, but she hasn't thought about ways to actually go for common wholes. They were still trying to go for the unit price. So behind Joel's choice here, he's thinking so much about some of the big ideas, the mathematical ideas that he wants his children to develop. One of them is proportional reasoning. That's going to be a mathematical idea on the landscape of learning. He's also trying to develop their ability to use the ratio table, to bounce back and forth on it. That's going to be a powerful model for equivalence. He's also trying to develop their ability to think about the need for a common whole, because he's preparing the way for them to eventually be able to do addition for fractions when they're going to need the common whole, and they're going to need to understand the equivalence with common whole. There's his landscape of learning. So as he thinks about fractions, he's thinking about developing a deeper understanding of equivalence, the need for a common whole, strategies of how I can use the ratio table, important models like the ratio table, and at the heart of all of that, deepening their understanding of proportional reasoning. There's his landscape. That's why he chose that problem. Now let's think, if you were Joel, what problem are you going to do tomorrow? Because it's so easy to take a rich problem that somebody might give you. You're a grade 6 teacher. Oh good, now I've learned about this Best Buy problem. I can go do it with my grade 6 class. But is that going to be helpful? You see, it's not just about helping children realize what they're doing. It's crafting the context in a way that is going to support their development. Turn to the person you're sitting next to and have a little bit of a conversation on that.
That's like find a ratio that maybe isn't involved in money. Standing there thinking about where.
Kathy, could we start with you? I was listening in a little bit on your conversation with Dennis.
Well, we're talking about two issues. One is the unit rate. If some kids are still stuck with that idea and haven't kind of thought about the other strategies, but we still want to push them to use other ways of solving this problem. So we've come to an idea that the problem needs to be similar and that it'll provoke this range, especially moving towards the common whole. Because if that's where he's going later down in terms of addition, the common whole is an important idea in equivalence. So one idea was, do we need the same context? Maybe, maybe not. But definitely the numbers need to be different. And the question is, again, given how much he crafted the numbers with you, Kathy, we have to think about the numbers. What are the relationships? And all the things that we pointed out here, we'd want to study that, like the same difference. Even the idea of same denominator or same whole, common whole, different parts, same parts, different denominator. We want to be able to craft that again, so we have to think about that.
All right, Kathy, that sounded like a nice plan. Other thoughts on that?
We kind of talked about that we have a sense that maybe this is the first time they've encountered sort of this kind of proportional thinking, so we would want them to work in a context where they could work again with this and sort of muck about with the numbers on the ratio table. But we were thinking that we might be important to pull them out of the context of money so that they start to see that this is true in other cases. So for instance, if we were working with maybe the context of a recipe or something where they were having to double batches or half batches or what have you, so they could start to work with that piece, but make the numbers a little challenging so that they're seeing it again. And yes, it's true not only with money, but it's true when I do this as well. So more practice with thinking in that proportional manner, but taking that money piece out. It's a comfort for them, but maybe they need to experience it in a different context to develop the thinking beyond it as not just true for money.
We were thinking to make the numbers a little bit nastier to discourage the unit rate idea, so that if you're going to have to do all this long work, well, now that I've seen I can do it with some other method, maybe it's easier if these numbers don't lend themselves well easily to your basic long division kind of thing. Would create that tone that you want to have happen.
Nice plans, all of them, I think, and actually very similar to where Joel goes. So let's take a look now at the problem that might be a nice problem to follow with. And actually many of the ideas that you came up with are quite similar to this one. At Bob's Best Buys, you can scoop your own mixture of birdseed and weigh it. He sells it by the pound. Bob also sells packaged birdseed with the weight marked on the bag. Some customers prefer to make their own mixture, others buy the package sizes. At the checkout, Bob weighs the bag and charges by the pound. The problem is that most customers want to know the price before they get to the checkout. So Bob thought he would post a chart that would tell people the price once they know the weight.
Take a moment to write down some key ideas that you noticed during this session with Kathy in terms of analyzing the mathematics inherent in the problem, anticipating a range of student responses to a problem, making sense of students' mathematical thinking, and developing a landscape of learning. Take a moment to write down some strategies that you will implement in your classroom for teaching mathematics through problem solving, such as identifying a cluster of mathematics curriculum expectations inherent in solving a problem, using a landscape of learning, coordinating students' sharing of solutions using a math congress, or designing math problems that relate to previous learning.
You have experienced some key strategies for studying teaching through problem solving. We encourage you and your colleagues to select one aspect of the webcast to study further. Replay the webcast in its entirety to activate collaborative professional discussion and inquiry about improving mathematics instruction and student learning. Visit www.curriculum.org for a complete listing of archived and upcoming webcasts.